In this video, we're going to be adding two new terms to our understanding of oxidation and reduction reactions, as well as look at the reason why we use those terms in the first place. So to begin, let's revisit the synthesis of water, which is the redox reaction that we use to begin this unit. Now, if we want to calculate which elements have been oxidized and reduced without looking at the number of electrons directly, we can simply assign oxidation numbers to every element in the reactants and products. Now, we know that the total oxidation number within a compound must be equal to the total charge of that compound, so that means that hydrogen and oxygen gas must have oxidation numbers of 0 because neither of them has any charge and there are no other elements to balance the charge. This is true with every element in its element form as long as you're not dealing with an ion. Now, with water, on the other hand, we can use the oxidation number rules. We know that oxygen is always going to have an oxidation number of -2 if the oxygen is within a compound, and then hydrogen is pretty much always going to have an oxidation number of +1, again, as long as it's within a compound with another atom. Now, if we compare hydrogen gas to hydrogen within water, we see a net change of +1 in terms of its oxidation number, which means that each hydrogen has lost 1 electron. And of course, we know that this is how hydrogen works because of its electronegativity, so no surprise there. Likewise, with oxygen, when we go from elemental oxygen to oxygen within water, we see a net change in the oxidation number of -2, meaning that oxygen has gained 2 electrons. Again, this is exactly what we expect. So therefore, we see that hydrogen is the oxidation reaction, while oxygen is the reduction reaction. Now, there's a different way of looking at it. In this reaction, we can say that because hydrogen gave away its electrons to oxygen, we can say that hydrogen reduced oxygen. If we simplify this to a more generalized redox expression of A and B, in this case, we can see that A is giving away its 2 electrons here. We see that these 2 electrons are being absorbed by B, meaning that A going to A with a +2 charge is going to be our oxidation reaction. So we can say in this case that A reduced B, and that A is therefore what we consider to be the reducing agent, which again is the chemical that causes the other chemical to undergo a reduction, meaning that the reducing agent is the one that actually does the oxidizing reaction and therefore becomes oxidized. So again, this terminology appears a little bit confusing, but remember that reduction is the gaining of electrons, meaning that because A gives away its electrons, it causes the other compound or the other element B to become reduced, and in the process of reducing the other element in this question, it becomes oxidized. So in the case of our water reaction, we see that hydrogen undergoes an oxidation reaction, and therefore, because hydrogen is giving its electrons away to oxygen, we say that hydrogen is our reducing agent. Now, conversely, if we look at this hypothetical, because B is taking away the electrons from A, we can say that B oxidized A. B took the electrons with A, causing its oxidation number to increase, and therefore we can consider B to be the oxidizing agent. Because again, B takes away the electrons from A, and as B gains 2 electrons, it is going to have a -2 charge, and because we're going from a charge of 0 to a charge of -2, B, the oxidizing agent, becomes reduced. So when we look at this in our actual reaction with water, we know that oxygen is taking away the electrons from hydrogen, therefore causing hydrogen to become oxidized. And because oxygen gains 2 electrons, let's write that out here. So oxygen takes away hydrogen's electrons in order to become reduced. But because oxygen pulls hydrogen's electrons away, we can call it the oxidizing agent in this case. Now here, this gives us a little hint about why we use the term oxidation at all, because oxygen is a very, very good oxidizing agent, because oxygen has a high electronegativity and is therefore very good at taking away other elements' electrons, causing itself to be reduced. And this is part of the reason why we use the term oxidation for the loss of electrons. And we can see that more evidently if we take a look at compounds as we change the number of oxygen. So if we take a look at carbon compounds, we can see a pattern when it comes to their oxidation number. So as with every element in their elemental form, elemental carbon has an oxidation number of 0. If we take a look at carbon monoxide, we can see that that's going to change because oxygen's oxidation number of -2 holds true, meaning that carbon is going to have an oxidation number of +2 in this case because there's only one other oxygen here. Now with carbon dioxide, which we looked at in the previous video, again, oxidation number of oxygen is -2. -2 times 2 is -4. And because carbon dioxide, like carbon monoxide, has no charge, carbon's oxidation number must be +4 in order to balance out the charge. So from carbon to carbon monoxide to carbon dioxide, we see a very clear trend. As more oxygens are added to carbon, the oxidation number increases. So what we can see as a different way of looking at this, we can see that elemental carbon has no bonds with oxygen. Carbon monoxide, the carbon has 3 bonds with oxygen, and in carbon dioxide, the carbon has 4 bonds with oxygen. So a different way of restating the statement is by saying, as an element makes more bonds with oxygen, the compound or the element that is bonded to oxygen becomes more and more oxidized as we increase the number of bonds with oxygen, and that's exactly what we see with these 3 compounds here. Now, of particular interest to organic chemists is the relationship that the number of carbon to hydrogen bonds has. Not hydrogen bonds, the intermolecular force, but literally a bond between carbon and hydrogen. So if we do the same experimentation, let's count the oxidation numbers with hydrogen and carbon. So hydrogen's oxidation number is +1. +1 times 2 is +2, meaning that in ethine, which is carbon with a triple bond with 2 hydrogens, the total oxidation number of carbon is going to be -2. -2 divided by 2, because there are 2 carbons, is -1. So that gives us a baseline here. Now if we try ethene, +1 is the oxidation number of hydrogen. +1 times 4 is +4, meaning that the total oxidation number of carbon in this case is -4, but if we divide -4 by 2, because there are 2 carbons, that means that each carbon has an oxidation number of -2. Next, we can try ethane, which is a single bonded carbon to carbon with 6 hydrogens. Again, +1 is our starting oxidation number for hydrogen. +1 times 6 is +6, meaning that total oxidation number of carbon is -6. -6 divided by 2 carbons gives us -3. And then if we go down to 1 carbon with 4 bonds with 4 hydrogens, again, +1 is our oxidation number of hydrogen. +1 times 4 is +4. Meaning that our carbon in methane has an oxidation number of -4. So with hydrogen, we see the exact inverse as the relationship with oxygen. So as more hydrogens are added to carbon, the oxidation number decreases or gets more negative, whichever you prefer. Now, if we look at the number of bonds that each carbon makes with hydrogen, in ethine, we see that each carbon is bonded to one hydrogen. In ethene, we see that it's 2. In ethane, we see that it's 3 hydrogens per carbon. And then in methane, we see that it's 4. So as an element makes more bonds with hydrogen, the element within the compound that is bonded to hydrogen becomes more and more reduced. So this relationship of oxygens and carbons relative to the number of bonds they make with other elements is another important reason why we use the term oxidation, referring to the loss of electrons. In the next series of videos, we're going to look at the quantitative aspect of electrochemistry and redefining the term spontaneity when it comes to electrochemical and redox reactions.